This is our 16th AP Chemistry class. Today is Monday, September 28th. The objective today is 2.2. Students will be able to represent the relationship between potential energy and distance between atoms based on factors that influence the interaction strength. So we're looking at potential energy, distance between atoms, and factors that influence that strength of attraction between atoms. So our first key point is a graph of potential energy versus the distance between atoms is a useful representation for describing the interactions between atoms. Such graphs illustrate both the equilibrium bond length, the separation between atoms at which the potential energy is lowest, and the bond energy, the energy required to separate the atoms. So again, I want to emphasize bond length is the separation between atoms in a bond, and the potential energy, or the bond energy, is the energy required to pull apart these atoms. So here we have an energy curve. Notice our potential energy is the y-axis, the bond length is the x-axis. So when we have two atoms and they're very, very close together, their nuclei, their positively charged nuclei, are repelling. So notice the potential energy is way up here because these atoms really want to move away from each other. So this is not a favorable arrangement, but we get to a point where the atoms, the nuclei of each of the atoms is attracting the valence electron of the other atom, but not really repelling the other nucleus. So there's this sweet spot where we have the lowest potential energy, and where that distance is will indicate our bond length. Then once we pull them apart, now they're no longer even attracting each other, and so the potential energy will become zero. They'll have no force of attraction between each other. And so there's this sweet spot that atoms exist at in molecules, that two atoms will bond together at this perfect distance that balances the repulsion between the nuclei with the attraction each nuclei feels towards the other one's valence electrons. So check for understanding. Which of the following statements are true? So again, this is a graph that shows the potential energy over a specific distance of two atoms. So at zero, we're right on top of each other, so the potential energy would be through the roof. They're really repelling each other. As we slowly pull them apart, each picometer, which is 10 to the negative 12 meters. So remember, we're dealing with atoms. We're on a tiny, tiny scale. We end up hitting this low potential energy around 70 picometers. So where they're at this point where the two atoms their nuclei are attracting the other valence electrons, but the nuclei aren't repelling each other like they are over here. So the energy required to pull these atoms apart now is around 450 kilojoules per mole, and the atoms will be at a distance of around 70. And as we pull them apart, now that energy becomes zero because they're no longer attracted to each other. Our second key point is that in a covalent bond, the bond length is influenced by both the size of the atom's core and the bond order, single, double, and triple. So when we talk about bond order, we're talking about, is it a single bond, is it a double bond, or is it a triple bond? Bonds with a higher order are shorter and have larger bond energy. So you can kind of see that here. When we have a CC single bond, it has a bond enthalpy of around 348 kilojoules per mole. When we have a double bond, it has a bond enthalpy of around 612 kilojoules per mole. And if we have a triple bond, we have a bond energy of around 837 kilojoules per mole. So as we increase the bond order from single to triple, we increase the bond energy. And so this is shown here. So we're talking about the distance between two atoms, and as we increase the number of bonds, those atoms will move closer and closer and closer together. So the bond length becomes shorter because there's more connection points. A nucleus is more attracted to the 3 negative charges than a single valence electron. So there's a closer attraction, there's a stronger attraction as we increase the bond order, and there's also a closer attraction. So the radius, the bond length, will decrease, as well as the the bond energy will increase. The potential energy diagram is given for C triple bond O. A student claims that the curve for C single bond O would be less deep, so it would have a lower potential energy, and would be shifted to the right of the curve of C triple bond O. Do you agree with this claim? Explain why or why not. So the student is saying that the C single bond O would be less deep and shifted to the right. So it might look something like this. So it's indicating that we have a longer bond length for a C single bond O, would have a longer bond length, which is true, and that's indicated because the lowest potential energy is more to the right than for the triple bond. And it would have a lower potential, it would have a less negative potential energy, which means it has a less bond energy. So it would be easier to break this bond than it would be to break this bond. So this is true. I would agree with the student because a triple bond is a stronger attraction, meaning the atoms are closer together, and it takes more energy to break that bond than a single bond. Check for understanding. The potential energy as a function of internuclear distance for 3 diatomic molecules, X2, Y2, and Z2, is shown in the graph above. Based on the data in the graph, which of the following correctly identifies the diatomic molecules, X2, Y2, and Z2? So we have hydrogen, nitrogen, and oxygen. Notice we are comparing two things. We're comparing bond length and bond energy. So hydrogen is H, and it will bond like this. Oxygen is O2, and oxygen has 6 valence electrons, so it forms a double bond. And nitrogen has 5 valence electrons, so it will form a triple bond with itself. Oops. I apologize, I have too many electrons. Let me erase these. Okay, so we're talking about this bond length. So a HH bond is going to be weakest and longest because it is a single bond. So it's going to be weak and it's going to be long. A OO bond is going to be a little stronger. And an N bond is going to be the strongest. We also need to think about what these atoms look like. So even though our hydrogen has the weakest bond, hydrogen only has 1 electron shell. So the radii of hydrogen are quite small. So X is going to represent hydrogen because it's got the weakest amount of energy and is the shortest because it only has 1 shell. O is a double bond and N is a triple bond. Both oxygen and nitrogen have 2 electron shells. So the difference between their bond lengths will just be because one is a double bond and one is a triple bond. So we have a slightly longer bond length and a slightly shorter bond length. The difference in strength of their bond length, of their bonds will be because one is a double bond and one is a triple bond. So we know that nitrogen as a triple bond is going to have a much stronger attraction. It's going to have it's going to take way more energy to pull apart these nitrogens, so it will have a lower potential energy or a more negative potential energy than oxygen. So the correct answer is A. Key point 3, Coulomb's law can be used to understand the strength of interactions between cations and anions. Because the interaction strength is proportional to the charge on each ion, larger charges lead to stronger interactions. And because the interaction strength increases as the distance between the centers of the ions decrease, smaller ions lead to stronger attractions. So the key here is that the larger charge, so if we have an ion with a +2 charge versus an ion with a +1 charge, a larger charge leads to stronger attractions, and the smaller ions, a smaller radius, lead to stronger attractions. So we're familiar with Coulomb's law. This is Coulomb's law. We're looking at the product of the charges and the radius. So if we have Fe2+ and Na+, these both repel each other, right? We would have a positive force, so they're pushing in opposite directions. So they would not have the greatest force of attraction. So when we're comparing B and C, the only difference is that iron has a +2 charge versus a +3 charge. And so therefore C would have the greatest attraction. So go ahead and check for understanding. The lattice energy of a salt is related to the energy required to separate the ions. For which of the following pairs of ions is the energy that is required to separate the ions largest? Okay, so so we're looking for the energy required to separate the ions to be the largest. So we want the strongest attraction. So hopefully you notice that these both have a plus and minus 1, whereas C and D have a 2 charge. So it can't be A or B because our charges in C and D are greater. So the only thing that's different between C and D is magnesium versus calcium. If you look at the periodic table, magnesium has 3 electron shells, whereas calcium has 4 electron shells. Magnesium is in period 3, calcium is in period 4. And so therefore the radius of magnesium is going to be smaller than the radius of calcium. And so this one would be correct because our distance between magnesium and oxygen is smaller due to the smaller size of magnesium compared to calcium's larger size. So the answer would be C.